1b over Fourier series. They're not too bad, especially because Dr. Noren provided a lovely chart at the end of your exam practice, which is really great because I solved all the problems without the chart and thought that the test was going to be like crazy bonkers hard, but it's not. So don't forget about the chart because it makes it so much easier and will save you a bunch of time. So what we have here is we're asked to find the Fourier series representation of this function over a given interval. So we know that our a sub naught equals 1 over p times the integral of negative p to p of f of x dx, and our a sub n equals 1 over p integral negative p to p f of x times our cosine of n pi x, and then we know our b sub n equals 1 over p negative p to p f of x cosine, oh, these all need dx's, cosine, oh, I'm sorry, this should be a sine. Or sine n pi x dx. Okay, so now we can start solving for the coefficients of what we need. So we have our a sub a 0, our a sub 0 is going to equal our split interval since our function is piecewise defined. So we have 1 over 1 because our p is 1 in this case, times the integral from negative 1 to 0 of 1/3 dx, and then plus the integral of 0 to 1 of x squared dx. Okay, evaluating this, you should get 1/3 x plus 1/3 x cubed, evaluated 0 and 1, and evaluating at negative 1 and 0. Okay, so when you do this, you obviously evaluate 0 and you get 0, and you have minus negative 1 over 3, so you have a positive 1 over 3, and then plus our 1 over 3, 1 cubed, so this whole thing equals 2 over 3. So we have our a sub 0 equals 2/3. Okay. I'm going to get rid of this. Okay, now we can start on our a sub n. Okay, for a sub n, we have this 1 over p, which is still going to be 1 over 1, and then times the integral from negative 1 to 0 of 1/3 cosine n pi x, and then plus integral from 0 to 1 of x squared cosine n pi x. And this is where it would get really horrible if you didn't have a lovely little chart, because I tried integrating it and it takes a long time. So I'm glad he's giving you the chart. It does make your lives a lot easier. So this, we don't really need a chart. There is an entry, but I feel like you can do it without it. So you get your 1 over 3 n pi, and then times your sine of n pi x, and then you're evaluating that at negative 1 and 0. But for this one over here, which is the horrible hard one, there is a direct entry for our x squared cosine. So let's see if I can get that pulled up. Okay, so for our x squared cosine, you can go right over here, and it actually just has it right. Ooh, I can highlight. Has it right there, and you can use it right off the chart, which is really great. So using that, We don't even have to evaluate it because that is for a definite integral from 0 to some number p. In our case, p is 1. So we are just going to plug in those values. 2, -1, in pi squared, n squared. Okay, so that is part of our a sub naught that we don't have to evaluate. But let's go ahead and evaluate this first part. So we have a sine function. So if sine function evaluated at 0, what happens here? So sine of 0 is always going to be 0. So our first one is 0, and then we have minus sine of n times pi, because we have this -1 here, so I guess negative n times pi. But any multiple of pi in a sine function is always going to give you 0. So all we really have for our a sub n is right over here. So we have our a sub n equals 2 -1n pi squared n squared. Okay, so we're one step closer, and we can go ahead and start on our b sub n. Okay, get that out of there. Okay, so for our b sub n, super similar because we're dealing with the x squared and the sine this time. So we have our b squared of n. It's going to equal our 1 over 1, because that's our p, times the integral from -1 to 0, 1/3 sine pi n x plus the integral from 0 to 1. Hey, can you just give me a minute? I'm in the middle of a video. Hey, guys, can you just give me 1 minute? Okay, I'm in the middle of a video. I can't really stop it. I'm doing my job. Idiot. Okay, so we have our integral from 0 to 1 of our x squared times our sine of n pi x dx. And I don't know if you've noticed, but I have a really bad habit of leaving off my dx, and don't be like me and try to remember. Okay, so for our b sub n, we are going to get a -1/3 pi over n cosine of n pi x, evaluated at -1 and 0, plus, and over here again looks horrible, is a horrible integration by parts thing. We can actually just go to our chart over here. So we're dealing with an x squared function, and we're evaluating from 0 to some known p. So we can actually just plug in these exact values, which is really, really nice because, like I said, it's a very nasty integration. Okay, so plugging in those values, we will get our -1 n plus 1 n squared pi squared -2 all over our n cubed pi cubed. Okay, and now all that's left to do in this section is evaluate this cosine. Okay, so what's going to happen here? So we start at our cosine of 0. What happens when we evaluate the cosine of 0? We get a 1, so we have -1 3 pi n, and then minus. And now we evaluate the cosine at a -1. So what happens when we evaluate cosine at -1? In this instance, we do a -1 to an n. This is another way of writing it. They really mean the same thing, but since the cosine fluctuates between -1 and 1, depending on whether n here is even or odd, this is a way of writing it where you don't really have to deal with a cosine, since it really does only fluctuate between those two values. So then we have 3 pi over n. Obviously, you can combine those. So for your whole thing, you should get -1 minus -1 to the n for 3 pi n, and then this whole thing. Okay, so I'm going to make that smaller, and then we can plug in all our values. Actually, I'm going to go ahead and write it over here if I have space. -1 minus -1 to the n, 3 pi n, -1 to the n plus 1. I'm really trying to fit this in. N squared, pi squared, -2 parentheses, bracket, all over n cubed, pi cubed. Okay, now I can go ahead and get rid of all of this, and we can write out our full solution. So all of this was to find a Fourier series representation of this piecewise function. So now we are going to plug it in to our base equation. So we have f of x equals a naught over 2, and plus the summation n equals 1 to infinity of our a sub n cosine n pi x, then plus our summation n equals 1 infinity of our should be a b sub n of our sine n pi x. Okay. Okay, so now we can actually just plug in the values that we have. So we get our f of x here, and then we found that a sub naught is 2/3, so 2/3 over 2 is just going to give you 1/3, and then plus this summation here is going to give you summation n equals 1 of -1 to the n times 2 n squared pi squared cosine n pi x, and then plus the summation here, n equals 1 infinity of our b sub n. Again, I think I'm actually just going to start it on this next line because our b sub n is kind of long for this one, and I don't think I can fit it all the way in. N plus 1 n squared pi squared minus 2 over n cubed pi cubed minus 1 minus -1 over n, raised to the n, 3n pi. And it's a little bit sloppy and unorthodox here, but that is the solution. And I can post a worked out on paper, so hopefully you can follow it a little bit better, but please let me know if you have any questions on this topic.